Today we will work with Chapter 17.2, Circles, in Analytic Geometry. There are two concepts we are going to familiarize ourselves in this chapter. One is recognizing an equation whose graph is a circle. That's the form of circles as an algebra equation. And the other concept is how to complete the square. Completing the square is an Algebra 1 concept, but it's usually something that happens fairly late in the year. You might not have remembered it or done it very frequently, so we're going to encounter it again today. And it's going to be very important that you pay close attention to that aspect of today's lesson so that you understand what's going on when we quote-unquote complete the square. All right, to get used to our concepts for 17.2. Let's look at problem 17.7. Find an equation whose graph is a circle with center 4, -5 and radius 3 square root 2. This problem is simply asking us to make an equation which has these two terms in it, 4 and -5 and 3 root 2 as the radius, and we'll be using concepts from the last section to accomplish this. So, how to graph this? Think to yourself what a circle is and what it would mean to have an equation whose graph is a circle. What is a circle? A circle is an origin point with a series of equidistant points from that origin called radii. So think of that distance between the center and each of those points. We know what the center point is, but each of those points can be different as long as they're the same distance from the center point. So we can use our distance formula here. And we know that the distance formula's answer will be the radius for any point on a circle. From our center point to any point on the circumference of this circle, the distance is 3 root 2. So we're going to use this fact to make a distance formula that works for every single point on this circle. So this point, let's call it xy. And this other point will be 4, -5. Obviously, it's not 4, -5 on my little diagram here, but that's neither here nor there. So x minus 4 squared plus y minus 5 squared equals 3 root 2. And there we go, we've solved our problem. But we can simplify this equation a little bit, so let's simplify it just a little bit by getting rid of our square root. To get rid of that, we square both sides. And squaring 3 root 2, first we're going to square the 3, which is 9, square the 2, and that becomes 2. So our equation for our circle is a term involving x squared plus a term involving y squared equals the radius squared. And this is the form of the equation for a circle. Let's abstract that out a bit so that we have the general form for an equation of a circle. And that's what problem B is about. Alright, so here's the general form of our equation. X minus h squared plus y minus k squared equals r squared. H, k, and r have to be constant, otherwise we're not dealing with a circle. I think this makes sense. The radius of a circle has to be constant, obviously. And h and k are the coordinates for what? They're the coordinates for our origin. And the origin of a circle also has to be constant. The x and the y, on the other hand, those can move about. As long as h, k, and r are constant, x and y will only be able to be locations upon the circumference of our circle. Alright, very good. I'm really glad to see the light bulbs going off in your head here. Let's move on to 17.8 and apply this newfound power. And in 17.8, we'll have to be completing the square. In this problem, we're going to find the area of the region that is enclosed by the graph of this equation. Alright, so apparently this graph, or the graph of this equation, makes an enclosed area. And before we go off guessing that it's a circle, we don't actually know that yet. So we need to put our equation in the form of a circle. That way we will have the radius without having to draw anything. Just by rearranging our equation correctly, we can find the radius, which is pretty cool. So let's begin by first getting this equation in the form of an equation for a circle. The first thing I want to do is I look at each of these terms, 2x squared, 8x, 2y squared, 16y, and 4, and I recognize that they are each divisible by 2. So I'm going to divide this whole problem by 2, divide by 2 on both sides, and simplify this entire equation a bit. So remember, we're trying to get this in the form of x minus h close parentheses squared plus y minus k close parentheses squared equals r squared. And I'm not seeing a good way to get our parentheses here. I can't simplify the x squared and the 4x in a way which gives me x minus something squared. Or at least there's no clear way to do it. And this is where completing the square comes in. Now, the phrase completing the square means that we have some terms which, if we finesse properly, will create something that we can defoil. That's the phrase I like to use, defoiling something. And this is a common occurrence. Even for you, as young algebraists, you should see the x squared minus 4x and know that if the next term, block off everything else, you would know that the next term, if it were something that you would see after completing the foiling of an equation. How can you complete the square? How can you get, what would you add so that this would be a 3-term expression which you could quote-unquote defoil? Give yourself a minute to understand how I found the 4, and I realize that that expression is the same as x minus 2 squared. This is what completing the square is, going from x squared minus 4x to x squared minus 4x plus 4, and then turning it into its squared form, x minus 2 squared. But notice if I'm adding 4 to this side, I can't just pull a 4 out of anywhere when I'm doing algebraic equations. I have to add 4 to the other side as well. So this other side will be 2 plus 4. Okay, let's look at y squared plus 8y. What plus what equals 8? Well, it's got to be the same number twice. It has to be 4. And I'm going to square that 4. This makes 16. That's kind of the process. So I have to add 16 to both sides. And then how do I defoil y squared plus 8y plus 16? What will that give me? There's our equation in the form of a circle. The hardest part there was completing the square, and so make sure you are careful in doing that. The process you do for completing the square is you take half of the coefficient before your variable, and then you square that. And that will be the integer you need to complete the square. Alright, so we found this. Now we need to find the radius. Which number here represents the radius? Well, 22 represents the radius squared. And what is the equation for a circle? Pi r squared equals the area. And 22 is r squared. So pi 22. Alright, so those are our two problems that introduce us to circles in analytic geometry. The last thing that we might want to do, just to make sure we're understanding this circle equation, is tell me what the origin of our circle is. Now, I know I made a mistake on the other equation. I didn't subtract twice like I was supposed to. This is supposed to be y minus -5, y minus -5. But don't tell anyone, please. What is the coordinates of the center of this circle? 2, -4. And what is the radius? You have the radius squared, but what's the actual radius? Square root of 22. All right. Very good, class. You have a great day.